Okay, so we got a proton, right? And the charge on a proton is 1.60 times 10 to the minus, whoops, my E has 4 things, 19th coulombs, okay? And the mass of a proton is 1.673 times 10 to the minus 27th kilograms. And this is all in the data packet, so it's in that front section. It's like, I believe, one of the first useful pages. Let's see if we can find that. Make sure that we're getting the right number there. Yeah, there we go. Okay. Okay, and let's see. So it's traveling. Now let me give you a clue. Draw a picture of it for this thing, right? Draw a picture of it going in this direction here. Okay, so it's just straight to the left. So these problems always have like two parts. There's this one, and then there's the one after, right? Okay, so let's draw a picture of this guy going to the left. Yeah, at one instant, right? Here's its velocity. Okay, now if it's going clockwise, that is, this guy is, its path is like this, there must be a magnetic force that's up the page, right? Okay. There must be a magnetic force for it to go clockwise, right? Let's figure out the direction that this magnetic field needs to be, right? So put your index finger to the left. Put your thumb up the page. I have my middle fingers pointing out of this page, so the magnetic field is definitely out of the page. Okay. Now, as far as to how to figure out this, right, what we're going to do is we're going to say that the magnetic force equals centripetal force. So QVB equals mv squared over r. Okay. And then what are we solving for? B. So B is going to be, we can cancel out one of the v's, right? So B is going to be mv over r. mv over rq. Okay, so my magnetic field is going to be 1.673 E minus 27 times 3.71 E6 divided by, what's the radius? 4.9 centimeters, so 0.049 meters. And then the Q is 1.60 E minus 19. Okay. I think I can do that. 673 E minus 27. 1 E6 divided by 0.049 divided by 1.6 E minus 19. And I get that it's 0.79168. Is that right? Did I get that right? So I would say that that's actually a 2. That should be a 2. Yeah? That's what I would say. Okay? Yeah. I think we did that right. Yeah, there we go. So that's Teslas, right? So 0.792 Teslas, right? And then out of the page, right? Out of the page, All right. Now, let's look at this thing, right? What electric field in what direction would make it go straight to the left in the previous problem? Now, this is the benefit of having drawn a picture of this thing going to the left and figured it out from there, right? So that means that we have to have a electric force that's down the page, right? if this guy is up the page, if the magnetic force is up the page, the counter force has to be down the page, right? So down the page is the direction of our electric field. And then the rest of this calculation is really simple, right? We say magnetic force, QVB equals EQ. The Q's cancel, and E is just VB, right? Equals, how fast is it going? 3.71 E6. And then our magnetic field is 0.79168. So take that number and multiply by 3.71 E6. And I get 2937160.625, right? Or 2.94 times 10 to the 6th newtons per coulomb. I think the reason why this is slightly different is that I probably, when I calculated this, I always use 1.602 times 10 to the minus 19th for E, for the elementary charge. That's my guess. As to why I'm slightly off, let's see if that works. Let's see, insert. Yeah, that's the difference. Okay, anyway, and then this is going to be down the page. Okay, 2.94 times 10 to the 6 newtons per coulomb down the page. All right.